There you go. Usually they have like that scene in Boston University where Mikey, you've seen it, right?
Yeah.
It's Mikey Sully that's in the that's how he gets a bad grade in his his group of, I forgot his sorority, but they just walk out. I'm trying to imagine this scene. Yeah.
It's been a minute since I watched the movie. Did you watch the TV show? The Monsters at Work.
Oh, that's a new short they have, huh?
It's a show. It's a full show.
Oh, it's on Disney Plus, right?
Yeah.
Yeah. Are you Disney guy?
Wow. Kind of. Not like super into Disney, but I can appreciate Pixar film. Have you seen anything on show? Have you seen what? Any Star Wars shows? I'm saying Star Wars shows. You've seen Mandalorian and I've seen other one. Have you seen that? They kind of have the involved. The feel good fans. I haven't gotten part of it's pretty good. It's pretty good. I liked it. I mean, I thought, yeah, work, but yeah, that's how I felt with it. But Andor's a bit slow. It's really well. Yeah. I've been told it's really good. I've been told it's a better Star Wars. More about the Empire is like the officers and everything. Yeah, and it's more of like a political drama. Yeah, it's more of a lot of political drama. So it's definitely more. I really yeah, I tried to watch Boba Fett. And I got about halfway through, and that was the last Star Wars thing I watched. Yeah, I couldn't finish on either. I was so excited. So I was like, oh, they should do a Boba Fett show. And they did it, and I was like, wow, this sucks. It wasn't good. It wasn't good at all. How? But I don't know. Bad writers. All I can say. I don't know. I was at the so I just yeah.
Yeah, I know. I can. But oh, you don't have to do it. You didn't have your own partner. See? Yeah. Oh, I think we're like the Red Sea. Yeah. That's what I did because of Europe. I'm like, oh, it's good. This one. That's we will talk. Oh my God. This ain't bread. Yes. One of the brownies both cupcakes from yeah, but they ran out. So this doesn't actually have a switch. So if you say you have to park. Got an 8.
It's not that bad, so-
You got it.
Oh, it's gonna send.
You're obviously.
Here. Look, man. Just up there. Yeah. Could be. Yeah, but- So.
The math that you
So I'm gonna read the and get started. The other thing is gonna do. But that's create. So I'm gonna show them that.
Oh, wait, we're talking with us?
No, this is this.
Oh. They got like 17.
Yeah. Good morning. Did you catch up on everything?
Oh, no, we're gonna validate. I spent great, but I was.
I did this one that I was just there.
Yeah, I don't know. I don't know. Huh?
Yeah, the one we actually look at and when we're about to start, you guys. No, but we're gonna have to figure out. All right, everybody, let's go ahead and get started. Your exams are over here. Once we start on the classwork, if you haven't already grabbed your exams, you can grab them. But for right now, we're going to start the lecture. And we're going to talk about magnetic fields. We're going to talk about a couple of things regarding magnetic fields. We're going to revisit magnetic forces. Okay, forces on moving charges, forces on current wires. And then we're going to look at how magnetic and electric fields are related. We're going to start diving into the reason why we study electricity and magnetism at the same time. As it turns out, they're very, very intimately related. And we're going to take a look at that today. So starting off with forces. We know that a magnetic force on a current carrying wire can be calculated using the Biot-Savart law Q, V cross E. No big surprise there, right? We've seen this before, and we've even talked about what we're going to start off talking about. We've talked about charges that move in a magnetic field that's perpendicular to their motion. If we have a magnetic field that is into the board, let's represent that with X's. So all of these X's represent magnetic fields. Just going directly into the board. However, we're creating magnets, we're creating them so they're in that direction. We get a big old iron magnet pointed towards the board, and that gives us our magnetic field. You might wonder what happens to a charge in this magnetic field. We discussed it last time. If we have a charge right here, charge Q. Well, if it's a positive charge and our positive charge is moving to the right, what way is the force going to be? B crossed into B says force is upwards, right? It's doing right-hand rule. Couple ways to do it. I've shown you the figure index finger pointing in the direction of the first vector, B. Middle finger points in the direction of the second vector, B. Thumb points in the direction of the fourth. Says the force is going to be upwards. And if we say the force is upwards, that means that our particle is going to be turning. It's going to be turning to move more upwards, right? Once it's at this point, it's going to feel force inwards, and it's going to continue as long as we're in the magnetic field, creating a circular path. Well, we've studied circular motion before, right? we studied circular motion, we said something about centripetal forces and centripetal accelerations. You guys remember back from last semester, how do you find the centripetal acceleration? Acceleration of just this object moving in circular. You guys don't remember? It was a while ago. V squared over the radius. Acceleration is V squared over R. Or any object undergoing uniform circular motion, much like this charge is. And we know that force is mass times acceleration. Newton's law says that. So we know F equals mass times acceleration. In this case, acceleration V squared over R. This is your centripetal force. You guys might remember that. In this problem, in this moving charge, our force is our magnetic force. F is equal to Q V cross B. But when we're calculating the cross product here, we could do this a couple of different ways. We could take the determinant of the matrix made up of the components of B and the components of B. We find the cross product that way. But it's a little bit more convenient in this case because if we look at our velocity and our magnetic field, at every single point, our velocity is always perpendicular to our magnetic field. Since it's always perpendicular, we can do an easier cross product. We can say the magnitude of velocity times the magnitude of the magnetic field times sine of the angle between those two vectors. Sine of 90 degrees is what? It's 1, absolutely. So we say mv squared over r is equal to q times the magnitude of b times the magnitude of b. The vector arrows up here. We get this relationship. This is the relationship that any charged particle moving perpendicular to a magnetic field. This is a relationship that will hold. Now, why is this something that we might care about? Why does this matter? Well, what we can do is we can solve for something interesting about this. We can solve for r. There's a number of reasons why you might want to solve for r. When we solve for r, what do we get? We get r is equal to m b squared b, one of the square b's cancel out, mv over q. I'm going to separate these fractions, put m over q by itself. We get that the radius is equal to m over q times b over, sorry, no, not r, b over b, b over the magnetic field. Now let's examine this. Let's examine this piece by piece. The more massive an object is, the larger the radius is. This should make sense to us. Larger objects have larger inertia. It's harder to turn a more massive object. So a more massive object will have a larger turning radius, right? Think about a large truck, and I say larger turning radius because it can't get that same centripetal force. The larger the charge, the tighter the radius will be. So if it has more coulombs, that means it's going to feel a larger force, meaning it's going to have a tighter radius. The faster it's moving, the larger the radius is. This also should make sense to us. If it's moving really fast, it's going to need a lot of force to get to turn. And B, if we increase the magnetic field, it's going to tighten the radius because it's going to make it a larger force. Now this property is used a lot, particularly in chemistry, because this m over q, this mass to charge ratio, this mass to charge ratio is something that is very specific characteristic to every type of element and molecule. Every element and molecule that has charge has this mass to charge ratio. So if we don't know what something is, if we don't know what this molecule is, what this compound is, but we know it has a charge and we know it has mass, well, we send that molecule into a magnetic field. We look at how it undergoes a circular arc. And from that circular arc, knowing its speed and its velocity, we can figure out its mass to charge ratio, figure out the mass to charge ratio, figure out what that thing is. This is the basis behind mass spectroscopy. Mass spectroscopy focuses on figuring out what is the mass to charge ratio. How many of us are in chemistry? How many of us have seen or heard about mass spectroscopy before? You guys are in chemistry, and you haven't, you will if you guys studying other things like kinesiology, you'll probably see it at some point. Mass to charge ratio is what mass spectroscopy focuses on. Very, very useful thing to know. Any questions about that? Not too bad, right? Okay. We spent some time looking at forces on current carrying wires, right? We said we have this wire. Our wire is in a magnetic field as well. And consistency, going to put the magnetic field into the board. And we said that this wire, this current carrying wire, is going to feel a force, right? After all, current carrying wire is just a bunch of charges moving, through a magnetic field. In this case, our charges are going to feel force. Our current is going to the right. Force is going to be I crossed into B, then up this right-hand rule. But how can we describe this force using more quantitative methods? Well, let's start with an examination. Force is equal to Q V cross B. Always going back to Biot-Savart. Force is equal to Q V cross B. Well, examining this V term. This velocity is the speed of any given charge in here. So we say we have some charge right here. I'm going to say this is some Q moving at some speed V, right? Well, that velocity is a description of how long it takes to travel a certain distance. So we say it's going to travel this distance L. It's going to take some amount of time delta T to travel that distance. So to travel distance L takes some time. So we can replace this velocity with just that. Q times length over time times velocity to V. And the length vector is the vector pointing in the same direction that our charge was pointing in. Well, I'm going to do a little bit of rearranging. Instead of doing L over delta T, I'm going to do Q over delta T. Charge over time, delta T times L cross B. And this Q over time. Well, this Q over time is just how many charges pass through the wire in a given time frame. So we put some imaginary cross section here. What we do, we count how much charge passes by there in some amount of time, delta T. That is exactly what a current is, right? The current is just how much charge passes through a wire in a given period of time, Q over delta T. So we get I times L cross B. Sometimes, and this isn't always going to be the case, but sometimes we change the vector arrow. So remember, L was in the direction of the moving charges. L is in the same direction as current. So sometimes we write this as force is equal to L times I cross B, where we say I is the vector. I is just the current in a given direction. Now, this isn't always going to be the case. This isn't always the proper way to do it, but it's the easiest way to think about what direction is left. Now, what direction are we looking at? We're looking at the direction of the currents. If we have a current carrying wire and we know what the angle between the current and the magnetic field is, we can simplify this to LIB times the sine of the angle that exists between the current and the magnetic field. ILB LIB sine theta. We know how to find that angle theta using dot products. We looked at that a while ago. This is the basic way to solve for the force on a current carrying wire. And this L This L is how much length is inside the magnetic field. So if our magnetic field only exists in this region, we only consider the length that is inside of our magnetic field. Anything outside the magnetic field doesn't feel any force because it's outside what's causing the force. Does that make sense? Do we feel okay about that? Okay. Now, I was going to show you guys a demo on forces on wires and magnetic fields, but the department's big ass magnet went missing. So you guys don't get that demo. Sorry. You guys will get a couple of demos today, and you'll get demos that show us the relationship between magnetic fields and electric fields. How is electricity and magnetism related? Why is this course titled Electricity and Magnetism? Why is it we always refer to both of them sort of at the same time? The reason why is they are very much connected. We think about how magnetic fields are created, and we said magnetic fields are created by moving charges, right? If we have a moving charge, we get a magnetic field. And you might think that the opposite is true. If a moving charge creates a magnetic field, perhaps putting a charge in a magnetic field will make the charge move. You know, if a current gives us a magnetic field, maybe a magnetic field will give us a current. And that's almost the truth. What is true is that a changing field, changing magnetic field results in a current. So if we have not a constant magnetic field, but if we have a changing magnetic field, we get a current. That means that we need some way to describe changing magnetic field if we want a way to describe our current. Now I want to justify this first thing. And this first thing was done by a physicist named Ampere, and he did just experimental work. He's asked this very question: will magnetic fields give us a current? So he built up a device. He said, all right, large coil of wires. There's no power source in here at all. And he said, all right, if I put a magnetic field in this, perhaps I'll get a charge. So he hooked it up to a very sensitive ammeter, such as what's here. This is called a galvanometer. Galvanometer is a fancy way of saying very, very, very sensitive ammeter. Will sense very small currents. So what he did is he took a magnet and he put it inside of the coil of wire. I'm going to go very slowly for a reason. Now there exists magnetic field in the wire. Put a magnet in there, there's a magnetic field. But we don't get a current, right? It's not deflecting either way. But he noticed something that when you remove the magnet, you get a deflection, right? And we're seeing this, right? See the deflection. So it seemed to be a changing magnetic field that gives us our currents. So he set out to describe how our magnetic field is changing, and he used something in mathematics called a flux. And the flux is just a description of how much stuff is flowing through an area, through a surface, right? In the case of a magnetic flux is how much magnetic field points through an area. Now I have to introduce something to you guys. I have to introduce the concept of a bivector or a two-vector. Two-vector is just a vector in multiple dimensions. So we think about regular vectors. Regular vectors point in a straight line, right? Lines are one-dimensional things. Bivectors are areas. They exist in multiple dimensions. And to demonstrate the concept of a bivector flux, problem is I'm going to attempt to draw this out first. So we need a surface and we define our surface, we say this is our surface with whatever area it has as an area based on its width and its height. And the flux phi, represent flux with the letter phi, is equal to how much magnetic field B is going through this area, this phi vector, this 2 vector. So we set up this surface and we look how much magnetic field passes through our surface. If we take this to be our surface, right? This ring right here, we imagine this is our surface. And we have our magnetic field. And represent our magnetic field with this meter stick. You can imagine the magnetic field going through our bivector. If our magnetic field goes through our surface, then we have a magnetic flux. However, if we orient our surface a little bit differently, our magnetic field will just skim across the top, not go through. 0 flux. Have some flux. So mathematically, we come up with a way to describe our surface in a way that will allow us to calculate flux. And how do we do this? Well, we use just the regular vectors stuff that we've learned. We treat our bivector just as though we're a regular vector. And our bivector needs a magnitude. And the magnitude of our bivector is just going to be the area of our surface. So in this case on the board, length times height, or width times height. Width times height gives us our magnitude. And then we need a direction. And the direction's a little bit more complicated because we need a way to consistently talk about the orientation of our surface, right? If we have a surface, we want to be able to describe the difference between if it were oriented this way or upwards. So we take the direction of our bivector to be in the direction that is perpendicular to our surface. So if our surface is oriented like this, perpendicular to our surface, straight up. So our direction is up. If it's oriented like this, take our direction to be to the right, down, towards you guys, always perpendicular to our surface. The direction is perpendicular to our surface. Perpendicular to our surface. Question. Okay. Now we have a little bit more freedom to use our mathematical skills because you'll notice that I wrote this as a dot product. B dot A. Well, B dot A can be calculated. We've learned before. BXAX plus BYB. AYBY plus Z. AZBZ. Or more simply, magnitude of A times the magnitude of the area vector times the cosine of the angle between them. Now we have to be careful here because the angle between them is not the angle between the surface and our magnetic field. I take our magnetic field, put it through the surface. This is not 90 degrees because our area vector is pointing towards the right in this case. So our magnetic field goes towards the right, area vector goes to the right, 0 degrees, right? Does that make sense? Yeah? If I say going straight down, well, our magnetic field is down, our area vector has a direction towards the right, 90 degrees. What does this mean? This means that cosine of 90 degrees gives us 0. So it's like this, 0 flux. Nothing is poking through our surface, right? 0 flux, no flux given. If we have an angle of 0 degrees, cosine of 0. Cosine of 0 is 1. So that means when we're perpendicular to our surface, meaning parallel to the direction of our area vector. We have the magnetic field just being magnetic field. The magnitude of, our magnetic flux is equal to the magnitude of our magnetic field times the area of our surface. So it all simplifies pretty nicely once we figure out what phi is. Give you guys a couple of demonstrations. Now I want to mention one more thing before I get to demonstrations. So we have a way to describe our magnetic field and how it's interacting with some area. If we wanted to know how this ends up creating a current, well, what creates current? Voltages create current, so somehow this is creating a voltage. And we get to what is known as Ampere's law. Ampere's law says that the voltage induced in a coil of wires, in a surface of wires, is equal to our changing phi d phi dt. You change the flux, you change the magnetic, you get a voltage. You get a voltage, you get a current. So ways to change our magnetic flux. I've shown you we can change the value of B. So we take this to be our surface area, right? This coil wire, our area is going to be the area that's the face of this coil wire. We can change the magnetic field. We can make it stronger by bringing a magnet close to it. We get deflection. Bring a magnet further away, we get current. We can also change the angle, theta, right? Changing theta gives us a changing flux. So we take this, we change the angle. If I were a little bit more quick about it, you would see the changing current. But we do see changing current just based on changing the angle the magnet's at, right? Yeah. This is how electric generators work, right? You have a magnet in here, you change the angle, and as you change the angle, you get a current. So basic electric generators. The other way to do it, this is maybe a little bit more difficult to do, but change the area. So if you have a coil of wire, let's say that this was a loop of wire. If this were in a magnetic field and suddenly this were to expand, then we would get a current. If it were to contract, we would get a current. This would be like if we had just some springy wire that we let go and we let go as it contracts, we would get a magnetic field or a current. So ultimately what this says is that voltages, something very much related to electricity, is related to magnetism. You create a magnetic field, you get a current. To show you this induced current, I want to show you this demonstration. Now what this is it's a bunch of wires tightly wrapped around a very, very heavy iron core. Iron core is a magnetic material, so the coil of wires will create a magnetic field. We've seen moving charges create magnetic field. But what becomes interesting is when we hook this into our power outlet. When we hook this into our power outlet, is that gonna blow up? It's going to blow up. No, it's going to create an alternating current. And here alternating current means changing magnetic field. Changing magnetic field means we get light. Light in our light bulb, which is not connected to any batteries at all. It's just coiled wire. Changing magnetic field gives us light. Now, you turn that off for a second. We've learned something else though, because current going around in a circle and circle and circle, well, that creates magnetic fields, right? So I take this metal ring, not magnetic at all. This aluminum ring, I'm going to put it in here. And I'm going to describe to you what's going to happen. We're going to get a magnetic field in this coil of wire that's constantly changing. That constantly changing magnetic field is going to cause a constantly changing current in here. That current creates its own magnetic field that is opposite to this one. And if you ever have held two magnets that are in opposite directions close to each other, you know they repel. So what's going to happen here? We're going to see a force carry this ring up the iron core. And Alex is going to so bravely stand near this device that is going to make probably a little bit of noise and get ready to catch this projectile.
Oh, no, yes.
And all of this is because a current was created inside of this loop of wire. What does that sound?
Yeah, then we go to the light.
Yeah, that's because the iron core is a lot looser up here.
Scary.
Yeah, a little bit.
Why does it be like, is it dangerous, like, to touch?
You want to touch it?
No, no.
Okay then.
I volunteer.
I volunteer. If you let it run long enough, it'll heat up and it'll get warmer.
Okay. Like alternative.
Mm-hmm. You want to plug it in for me, Alex?
I have a quick question. Is it only magnetized when it has current going through it?
Yeah.
And then once it leaves it, the iron loses the magnetism?
And it draws back down.
Yeah, it does that because it's not going to be exposed to like a constant magnetic field. The magnetic field that's created in the coil is alternating currents, always changing direction. So it's not going to get a strong constant magnetic field. It's just always getting a very quickly changing magnetic field. So it will retain some weak amount of magnetism, but nothing too large. Go ahead and turn it on. Okay, you want to come up here? You can leave it on. You will feel the current moving through this. Come over here. Come over here. Hold the ring and put it over the wire, and you feel it start to heat up because of the current running through it. Oh, yeah, just feel it vibrating. Can you feel the warmth? Slowly, yeah. So you're feeling warmth because the current moving through the wire heats it up. Round of applause for our lovely. All right. Are there any questions, any comments, concerns before we start up with our classwork? Okay, I believe our classwork is on Canvas. I don't know why that's not. All right, give me a second and I'll get it up on the board. I'll get the classwork QR code up on the board. It is on Canvas. Just don't know why this isn't. There we go. So your classwork involves a little bit of everything that I've shown you. You're going to calculate some magnetic forces on some various things, and then you're going to calculate induced voltages. Induced voltages are also referred to as induced EMFs. If you remember back when we talked about batteries very briefly, I mentioned that we call the voltage supplied by batteries EMF. You can think of EMFs and voltages as the same thing in this class. If you have any questions, call over your TA or myself, and I'd be happy to answer. Hey, I want to see if it's very clear.
So, great questions.